Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Within the grand tapestry of 17th century mathematics, a period of explosive creativity and burgeoning analytical power, certain works stand as monumental pillars, bridging the ancient world of geometric certainty with the nascent universe of infinite processes. John Wallis' 1665 masterpiece, Arithmetica Infinitorum, is preeminently such a work. It is a text of breathtaking audacity, a testament to the power of analogical reasoning and inductive leaps in the absence of formal proof. For a modern reader accustomed to the exacting standards of rigor established by Cauchy and Weierstrass, Wallis' methods can appear almost scandalous, a form of intellectual recklessness. Yet, to dismiss his work on these grounds is to fundamentally misunderstand its pivotal role. The Arithmetica Infinitorum was a powerful engine of discovery, a work that, through its very imperfections and speculative brilliance, cleared a path directly for the innovations of Isaac Newton and the formalization of the calculus. It represents a profound shift in mathematical thinking, where the rigid constraints of Euclidean geometry give way to the boundless possibilities of algebraic analysis, a moment when the arithmetic of the finite was daringly extended to conquer to appreciate the revolutionary character of Wallis' contribution, one must first survey the intellectual landscape he inherited. The problem of quadrature, the calculation of areas bounded by curves, had for millennia been the domain of geometry. The gold standard was the method of exhaustion, perfected by Archimedes. This technique involved inscribing and circumscribing polygons within and around a curve, demonstrating that the area of the curve was the unique value squeezed between the areas of the two polygonal sequences. The method was logically unimpeachable, a marvel of deductive reasoning. Its profound limitation, however, was its synthetic nature. It required a pre-existing intuition of the answer, which the method could then rigorously confirm. It was a tool of verification, an unwieldy one, offering little in the way of a general procedure for discovery. The early 17th century saw the emergence of a more potent, if philosophically troubling, alternative, the method of indivisibles, championed most famously by Bonaventure Cavalieri in his 1635 Geometria Indivisibilibus. Cavalieri conceived of an area as an infinite collection of parallel line segments, or indivisibles, and a volume as a collection of planes. By comparing the sums of these indivisibles for different figures, he could deduce relationships between their areas or volumes with astonishing efficiency. He could, for instance, demonstrate that the area under a parabola was a specific fraction of its circumscribing rectangle. The method's power was undeniable, but its logical foundation was precarious. The concept of an area being composed of one-dimensional lines, which themselves have zero area, provoked intense debate and criticism. Figures like Pierre de Fermat and Gilles de Roberval were also developing their own ad hoc techniques for quadratures and finding tangents, methods that hinted at the calculus to come but remained a collection of clever, disconnected procedures. This Wallis entered a world rich with new truths but lacking unifying, systematic algebraic language to organize. The Arithmetica Infinitorum proposed a radical departure from these geometric leanings, championing a methodology rooted entirely in the patterns of arithmetic and algebra. Wallis' central technique was a bold form of incomplete induction. He would begin by calculating a series of simple, known cases, arrange the results in a sequence, and then extrapolate a general law governing the entire sequence. His most celebrated application of this method was his investigation into the area under curves defined by the equation y equals x to the power of k, or what we would today express as the integral from 0 to 1 of x to the power of k dx. He started with integer exponents. For k equals 0, the area is that of a unit square, which is 1. For k equals 1, the area is a triangle with area 1/2. For k equals 2, the case of the parabola, he used Cavalieri's principle to find the area as 1/3. For k equals 3, he found the area to be 1/4. Wallis arranged these results and observed an unmistakable pattern. The ratio of the area under the curve to the area of the circumscribing unit square was consistently 1 over the quantity k plus 1. Herein lies Wallis' great intellectual leap. Possessing this pattern derived from positive integers, he made the audacious assumption that this rule must hold true for all exponents, including fractional and negative ones. This was a profound conceptual move. The very idea of a fractional exponent was a relative novelty, and to treat the series of exponents as a continuous domain wherein a pattern discovered for integers would persist was an act of profound faith in the uniformity of mathematical structure. He was transforming a geometric problem of area into a purely numerical problem of sequence completion. By doing so, he effectively calculated the areas under a vast new family of curves without recourse to any geometric diagrams or indivisibles, relying solely on the power of algebraic analogy. This was the arithmetic of infinites in action, a systematic algorithm that replaced the bespoke methods of his predecessors. It was a clear demonstration that the emergent language of algebra could be a more powerful tool for discovery than the classical language of geometry. The pinnacle of this approach, and the most enduringly famous section of the Arithmetica Infinitorum, is Wallis' attempt at the quadrature of the circle. This ancient problem, in his new analytical framework, was equivalent to finding the area of a quarter circle of unit radius, a value we know to be pi/4. This required evaluating the integral from 0 to 1 of the square root of the quantity 1 minus x squared dx. The exponent in this case, 1/2, fit his generalized scheme. However, a form of the expression itself, a binomial, resisted his direct method. Undeterred, Wallis exhibited his characteristic ingenuity by inverting the problem. He considered a more general family of integrals involving expressions of the form 1 minus x to the power of 1/p, all raised to the power of q. His goal was to find the value when p equals 2 and q equals 1/2. What followed was a masterful use of interpolation, a technique that stands as his most significant methodological contribution. Wallis constructed a large two-dimensional table of the values of these integrals for various integer values of p and q. This table revealed elegant numerical patterns running both horizontally and vertically. He had columns of results for parabolas and rows of results for other related curves. The space in his table corresponding to p equals 2 and q equals 1/2, the value for the circle, was empty. Wallis treated the calculated values in his table as discrete points on a continuous surface. His task, then, was to guess the value that should occupy the blank space by interpolating from the surrounding known values. This intricate process of numerical exploration, of filling in the gaps in his table, led him through a series of complex ratio calculations. The astonishing result of this interpolation was a completely novel and unexpected formula, an infinite product for pi. He expressed the ratio of the area of the unit square to the area of the inscribed circle, which is 4/pi, through an infinite sequence of rational numbers. Rearranged, this yields the celebrated Wallis product. Pi/2 equals the infinite product of the terms 2/1 times 2/3 times 4/3 times 4/5 times 6/5 times 6/7, and so on in a cascading sequence. This was a moment of profound mathematical revelation. The transcendental number pi, a constant defined by the geometry of the circle, was shown to be constructible from a purely arithmetic sequence of integers. Geometry had been fully translated into the language of infinite arithmetic. The publication of the Arithmetica Infinitorum sent ripples through the European scientific community. Its power and the breadth of its results were immediately recognized. Yet, its methodology provoked deep suspicion. The reliance on induction and analogy, without any semblance of deductive proof, was an affront to the sensibilities of many mathematicians. The acerbic philosopher Thomas Hobbes, already engaged in a long-running feud with Wallis, famously derided his symbolic methods as a scab of symbols and a scurvy book, arguing that they abandoned the clarity and certainty of geometry. Even a more sympathetic and brilliant mathematician like Christian Huygens expressed significant reservations at acknowledging the correctness of Wallis' results while finding his path to them logically unsound and perilous. For these thinkers, Wallis had achieved his conclusions through a form of inspired guesswork, a path that was unsuitable for the secure foundations of mathematics. The work's most consequential reader, however, was a young student at Cambridge named Isaac Newton. Newton studied the Arithmetica Infinitorum with an intensity that bordered on obsession, absorbing its techniques and, crucially, identifying its core creative principle. He wrote later in life that Wallis' work was a primary stimulus for his own early mathematical investigations. Newton took the central idea of interpolation and elevated it to a new plane of abstraction. Where Wallis had interpolated a numerical value from a table of numbers, Newton sought to interpolate an entire algebraic formula. He applied this thinking to the binomial expression 1 plus x, raised to a given power, by examining the patterns of the coefficients for integer powers, famously represented in Pascal's triangle. Newton generalized the formula to accommodate fractional and negative exponents. This led to his discovery of the generalized binomial theorem, one of the foundational tools of analysis. Armed with this theorem, Newton could now attack the quadrature of the circle in a way that was both more powerful and more systematic than Wallis. He could expand the expression the square root of the quantity 1 minus x squared into an infinite power series. He could then integrate this series term by term, using Wallis' own rule for powers of x to produce an infinite series for the area of the circle, and thus for pi. This was a direct and brilliant extension of Wallis' program. The numerical interpolation of the Arithmetica Infinitorum became the algebraic interpolation of Newton's method of fluxions. In conclusion, The legacy of John Wallis' Arithmetica Infinitorum is complex and profound. It is a work that stands as a monument to the transitional state of 17th century mathematics, a field brimming with creative energy yet to be constrained by the rigorous logic that would later define it. Wallis' cavalier approach to proof, his willingness to leap from finite data points to infinite generalizations, and his unshakable belief in the power of algebraic patterns were the very qualities that made his work so generative. He provided the crucial bridge from the discrete, case-by-case methods of Cavalieri and Fermat to the systematic, algorithmic power of Newton and Leibniz. The Arithmetica Infinitorum, with its famous product for pi and its iconic symbol for infinity, did more than solve problems. It changed the very philosophy of what it meant to do mathematics. It asserted the primacy of algebraic analysis and demonstrated that the secrets of the continuous, of the infinite, could be unlocked through the careful, if audacious, manipulation of numbers and symbols, while its methods might appear as a scab of symbols to a classical geometer. For the generation that followed, they were the very seeds from which the calculus would grow.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.